Today we are going to discuss Chapter 15, the law of large numbers and the central limit theorem. As usual, I have posted this lecture note on Canvas, so please go ahead and download that and you can watch the video thereafter and complete the blanks with me. The central limit theorem is the most important theorem of all of statistics. All our future materials will be based on the central limit theorem. Therefore, understanding the central limit theorem at this point itself will be extremely important for the success of this class. On the other hand, the central limit theorem, the proof is actually very difficult. The proof of the central limit theorem is discussed only at graduate school level. We are an intro statistics class. Therefore, we will not discuss the proof of the central limit theorem. On the other hand, understanding the concept behind the central limit theorem is very straightforward and easy to understand. Okay? Before working on the central limit theorem, there is one other additional theorem that's considered important, which is called the law of large numbers. That's what I have written down under point number 1. Let's look at the law of large numbers. This is abbreviated as LLN. Law of large numbers. There's a small connection between the law of large numbers and the central limit theorem. That's the reason why we first discuss the law of large numbers. The sample mean, or x bar, is an estimate of the true mean or the population mean, which is a parameter given by mu. Now here's a law of large numbers. When you increase the sample size, the calculated sample mean, which is x bar, becomes more and more reliable as an estimate of the true population mean parameter mu. Very easy to understand, and it makes complete sense. When you have a larger sample, the calculated statistics are more reliable than the calculated statistics from a smaller sample. That's it. So let me write it down as that. I will say let x bar be the sample mean calculated using a sample of size n. So the law of large numbers says that as n increases, the reliability of x bar as an estimate of mu, which is the population parameter mean, increases. Okay? So here's the law of large numbers. As n increases, the reliability of x bar as an estimate of mu, which is the true mean, mu is a parameter, increases. Very easy to understand. Here's an example given under point number 2. A sample of size 20 gives an estimated sample mean of 104.5, and a sample of size 30 gives an estimated sample mean of 106.2. Which of the following statements holds true according to the law of large numbers? A. 104.5 is more reliable than 106.2. B. 106.2 is more reliable than 104.5. C. Both 104.5 and 106.2 are equally reliable. The answer is B. 106.2 is more reliable than 104.5 because 106.2 was the calculated mean using a larger sample of size 30 compared with 104.5, which was calculated using a smaller sample of size 20. Now we are in a good shape to move into the central limit theorem. Point number 3, the central limit theorem. The central limit theorem is abbreviated as CLT. Now here's the central limit theorem. I will let x be a random variable technically from any distribution. I will let x be a random variable from any distribution for any distribution. We know how to calculate the mean and variance. Okay? So I will add one additional part. Let x be a random variable from any distribution whose mean equals mu and variance equals sigma squared. Now this x could be whatever the quantitative random variable. It could be a discrete random variable and it could be a continuous random variable. For example, it could be the number of vehicles entering a parking lot. In that case, it's a discrete random variable. And x could be the wind speed or the weight or the temperature. In such cases, x is a continuous random variable and so on. You know the difference between them, right? Good. What I'm going to do next is I'm going to take samples of size n from that random variable. Take samples of size n and I will let x bar be the calculated sample mean. Now these symbols are not new. We've seen using lowercase n for sample size many times and x bar for the sample mean. The mean of the original random variable x is equal to mu and the variance of this original random variable is equal to sigma squared. Now remember we said x could follow technically any distribution. Any distribution, okay? Could be uniform distribution, could be the chi-square distribution, F distribution, T distribution, okay, discrete distribution, Poisson distribution, and whatever the other distributions available. X could follow technically any distribution. Now the central limit theorem tells us the distribution of x bar. The central limit theorem says that the distribution of x bar, no matter what the distribution of original x is, x bar will essentially follow a normal distribution. For the normal distribution, there are two parameters. One is the mean, the other one is the variance. First, we write the mean and then we write the variance. The mean of that normal distribution will be equal to the same mean of the original random variable x, which is mu. The variance, on the other hand, will be slightly different. The variance will be the variance of the original random variable x divided by the sample size. So the variance will be sigma squared over n. That's the central limit theorem. It's very important to remember the central limit theorem. There's technically no other more important theorem in statistics than the central limit theorem. Please remember the central limit theorem for the rest of this semester. It's going to be very important for all the future calculations, and all the future materials will be built based on the central limit theorem. Then we can move on to point number 4. There I have a simple example. A population of 29-year-old males has a true mean salary of 48,052. That means we will let x be the random variable of the salary of 29-year-old males. the distribution of x is not given, but they say that the true mean is $48,052. Okay. So true mean, which means mu for random variable x, is $48,052. And the true standard deviation of 3,120. That means sigma equals 3120. If a sample of 100 29-year-old males is taken, that means n equals 100. Those are the pieces that you should identify when you read those questions. Okay. Sample size is 100. What's the probability that their mean salary will be greater than 49,000? I need the mean salary. Distribution of the mean salary will be required to find that probability. Okay? So the question is, what's the probability that their mean salary, not the salary? X is the salary. So the mean salary will be X bar. Okay? So X bar should follow a normal distribution according to Central Limit Theorem. With the same mean as the original random variable, which is 48,052, what should be the variance? The variance should be 3120 squared divided by 100. Okay? 3120 squared divided by 100. Well, this term can also be simplified as, okay? So this term can also be simplified as 312 squared. All right, so what I need now is the probability that X bar could be greater than 49,000. I need X bar to be greater than 49,000. Now that's very easy to find. We have the distribution of X bar, which is centered at 48,052. And this given value is 49,000, which will be somewhere here. Greater than that, which means I will need area to the right from this point, correct? So I have to go to distributions in your calculator, select number 2, normal CDF, and the lower limit is 49,000, upper limit is something positively large, 100 million for example. Mu equals 48,052. Sigma, what should be sigma? This is variance, okay? 312 squared is variance. So you have to enter sigma. Variance means sigma squared. Sigma means the standard deviation, or in other words, the square root of the variance. So I will enter sigma as 312. Let's go to your calculator. I have to go to distributions, which I can access by pressing second and variables. That's where we have distributions, and then I have to select number 2, normal CDF. Select that and hit enter. The lower limit this time is 49,000. The upper limit is something positive and large, like 100 million. Mu equals 48,052. Sigma equals 312. Select paste and hit enter. In case if you see normal CDF and open parentheses in your calculator screen instead of this full breakdown, you have to enter these numbers in this order separated by a comma. Where's the comma? Comma can be found right here in the key above key number 7. And then you have to close parentheses and then you can hit enter. In this calculator, I can just select paste and hit enter again. 0.0012 is the answer we need. I got 0.0012 approximately to the 4th decimal place. All right, so that's an example. There's a message given in that example. When you read the question, read carefully to identify the random variable. In this example, the random variable is the salary of 29-year-old males. These values, mu, sigma, and n, should be given for that random variable. Of course, mu and sigma are for the random variable, and n is the sample size. So identify those things, and then read the rest of the question carefully. So here, the random variable is salary. The question is not about any probability regarding the salary. If it was about a probability regarding the salary, I don't have to go for the central limit theorem, okay? I will still need the distribution of x. In this example, the distribution of x is not given. The probability I need to find is not the salary being greater than 49,000, but the average salary being greater than 49,000 is what I need. So I have also underlined the mean salary for your attention in this example, okay? That means the probability I need is not about x, but about x bar calculated using samples of 100. That's the reason I used the distribution of x bar as given by the central limit theorem, okay? Always pay attention to x and x bar, the words defining them, okay? Random variable is x. Mean of that random variable is x bar, okay? That's very important. Why did we discuss the law of large numbers before talking about the central limit theorem? Central limit theorem will almost always hold true, but it holds true properly when n is large. Of course, when n is large, x bar is better. Reliability of x bar as an estimate of the true mean mu increases. That's the law of large numbers. Let's go to point number 5. Question given under point number 5 is an electronics company manufactures resistors that have a mean resistance of 100 ohms and a standard deviation of 10 ohms. The distribution of resistance is approximately normal. It doesn't have to be, but it's given as that. So we're going to use that information. Part A, what's the random variable x? Write the distribution of x using the standard notations. That's very straightforward, and we've seen so many of these kind of calculations under the discussion of distributions. So, point number 5, part A. The random variable is resistance. The distribution of x is given. It's a normal distribution, it's given as that, with a mean of 100 and a variance, the standard deviation of 10, which means variance of 10 squared. Okay? So here, what you have to understand is your mu equals 100 and sigma equals 10. This is sigma squared. All right, let's move on to part B. If you choose one resistor at random, what's the probability that the resistance is lesser than 95 ohms? You choose one resistor at random. Now, am I supposed to go for the central limit theorem? No, this is just from the given random variable. I just have to pick one resistor. So I need the probability of that randomly selected resistor has a resistance of lesser than 95. So how can you find that? In order to find that, I seem to have to use this distribution. Okay? The distribution here is a normal distribution. Center is 100. So 95 should be somewhere here to the left. And lesser than that. That's the probability I need. We can easily find it. We can use your TI-84 calculator. Go to distributions. Select number 2 normal CDF. The lower limit will be something negative 100,000. Upper limit is 95. Mu equals 100. Sigma equals 10. And that's all you need. Let's go to distributions. Second, variables. That's where we have distributions, and select number 2 normal CDF. Hit enter. The lower limit is negative infinity. What I have on this screen is negative 1 E99, which means negative 1 times 10 raised to the 99.
which is good as the lower limit. And if you don't see that, you can simply enter a negative large number, use the key left of enter key for the negative symbol, and then you can enter 100,000 or so. The upper limit is 95, mu equals 100, sigma equals 10, and then we can select paste and hit enter. And we already know that if you don't see this breakdown in your calculator, normal CDF function, you have to enter these numbers separated by commas. The comma can be found in the key above key number 7, and then you have to close parentheses and then hit enter and hit enter again. The answer we need is 0.3085.
I got 0.3085. Let's move on to part C. Take a random sample of 25 resistors. So n equals 25. What should be the distribution of the average resistance X bar? Very clear. Question is very clear. I need the distribution of X bar. That should follow a normal distribution according to the central limit theorem. Okay, that's where the central limit theorem comes to play. So X bar should follow a normal distribution. What should be the mean? Mean should be the same mu, 100. And what should be the variance? Earlier the variance was 100, 10 squared, that divided by the sample size, which is 25. So n is 25. So sigma squared is 100, n is 25, 100 divided by 25 is 4. So the variance of X bar is 4, which we can write as 2 squared. So that 2 is the standard deviation. Part D. For samples of size 25, what's the probability that the average resistance would be lesser than 95? That means I need a probability regarding X bar, average resistance. That should be lesser than 95. I need that probability. So how do you find that? Just like earlier, I have to go for the distributions. X bar follows this distribution, which is centered at 100. So 95 will be somewhere here to the left. And again, I need this area. Now that probability will be different. Okay? It will be different compared with the answer of part B, because I have a different standard deviation. So we can go to distributions again and select normal CDF. And your lower limit will be negative 100,000, upper limit will be 95, mu will be 100, sigma will be equal to 2. And that's all you need.
Here's the calculator again. I don't even have to show this calculation to you. We have seen it so many times before. But anyways, I'm going to show it to you real quick. I'll go to distribution second, variables, and select number 2, normal CDF, hit enter. The lower limit is negative infinity, or you can have negative 100,000. Upper limit is 95, mu equals 100. This time, sigma is equal to 2. Select paste and hit enter again. The answer is 0.0062.
0.0062 as the answer. And then part E, for samples of size 25, what's the average resistance so that only 10% of resistors will have more average resistance than that. Now for that part, the probability is given to us. We need to do the inverse calculation. Okay? And that given probability, is it a right tail or an upper tail probability, or is it a lower tail or a left tail probability? We have to read carefully. So that only 10% of resistors will have more average resistance than that. Only 10% will have more. The term more indicates that given 10% is an upper tail, or in other words, right tail area. Okay? So it's the same distribution for X bar because it's about average resistance. So the distribution is symmetric and centered at 100. The given 10% is on the upper tail. So this is that 10% given, which is 0.1. What I need is this value. It's a value for average, X bar value. How do you find it? We have to go to distributions. This time select number 3, inverse normal. Okay? And the area, well, if you are using an older version of the calculator, you will have to enter 0.9 as the area because that's the area to the left. Version I'm using is a newer version, so I can enter any area and select the tail as right tail. So I can straight away enter 0.1 as the area, and then you have to enter mu and sigma, and then that's all.
Go to distributions again, second variables, that's where we have distributions. And I'm not going to select number 2 normal CDF. I have to do the inverse calculation this time. Therefore, select number 3 inverse normal. Hit enter. The area. In this calculator, on the 4th line, I can define whether the entered area is a left tail area or a right tail area or a center area. But most of the older versions of this calculator doesn't have that option. In all those calculators, you have to enter area as area to the left. Given area, which is 0.1, is an area to the right from a given point. Or in other words, it's a right tail area. If I enter 0.1, and then in the 4th line, I can select right as the tail. But for your calculator, in case if you don't have that option to select the tail, you will have to enter 0.9 as the area. Why? In this function, in those older versions of the calculator, area means always area to the left. Since the given area is 0.1, which is an area to the right, the area to the left from that point should be equal to 0.9. Because the total area is always equal to 1 unit. So the area to the left should be equal to 1 minus area to the right, which is 1 minus 0.1, which is equal to 0.9. But I'm not going to enter it as that. I will just enter area as 0.1, mu is equal to 100, sigma is equal to 2, and then I will select the tail as right. Select right and hit enter so that the tail area is permanently selected. Select paste, hit enter, and hit enter again. The required answer is 102.56.
So I got 102.56 ohms. Okay. Yeah, that's it about that question. And let's go to question number 6. Problem number 6. The number of flows in a fiber optic cable follows a Poisson distribution with lambda equals 1. Part A, what's the random variable x? Write down the distribution of x using the standard notations. Very straightforward. This time our random variable x is number of flows, and we have x follows Poisson distribution with lambda equals 1. That's it. Now for this distribution, what are the mean and the variance? For the Poisson distribution, which has lambda as the parameter, we know that mean equals variance equals lambda. Now for this example, lambda is equal to 1. So we have mean, which is mu, equals 1, and also sigma squared equals 1, which also means sigma equals 1. Okay, good. We'll need those two pieces when we work the central limit theorem part of this example. Okay. Part B, choose one fiber optic cable at random. What's the probability that the number of flows will be greater than or equal to 2? Choose one of them, and I need the probability that x will be greater than or equal to 2. Now, can you find this probability straight away using your calculator? The calculator doesn't have an option for the right-hand probabilities with Poisson CDF. Poisson CDF will only calculate left-hand probabilities. Okay. So, I have to first calculate a left-hand probability. What is that probability? Poisson distribution is a discrete probability distribution. Okay. So, for discrete probability distributions, we have an equation. Probability x greater than or equal to k plus 1 will be equal to 1 minus probability x lesser than or equal to k. Remember, this is only for discrete probability distributions. For continuous probability distributions, if you use this equation, your answer will be completely incorrect. We know Poisson distribution is a discrete probability distribution. That's the reason we are going to use this equation. Okay? So x greater than or equal to 2 should be equal to 1 minus probability x lesser than or equal to. Now the left hand side of this equation is k plus 1, the right hand side is k. So it is 2 on the left hand side, I must have 1 on the right hand side. And I can find that probability using your calculator. Okay? We have to go to distributions and select Poisson CDF. Okay, let's go to your calculator.
Let's go to distribution, second variables, and then I have to scroll down until I see Poisson CDF. You can see E is Poisson CDF. Select E, Poisson CDF, hit enter, and then I have to enter mu. This mu is the Poisson parameter lambda. That's the symbol used in this calculator for some reason. And some other versions of TI-84 calculator, you can see lambda instead of this mu. The lambda value was given as 1 for that example, and our x value is also equal to 1 because I need to find the probability x is lesser than or equal to 1. Select paste and then hit enter and hit enter again. The required answer is 0.7358.
This value I got 0.7357, and that has to be subtracted from 1. 0.2642. Let's move on to part C of that question. Choose 3 fiber optic cables at random and calculate the sample mean x bar. What should be the distribution of the average number of flows x bar? Okay. The sample size is 3. Now, to answer that question, I'm going to use the central limit theorem. X bar, according to the central limit theorem, should follow a normal distribution, no matter what your distribution for the original random variable x is. Okay? So x bar should follow a normal distribution with a mean of same mean as the original random variable, which is 1 for this example, comma, variance of the original random variable divided by sample size. So the variance of the original random variable is equal to 1, sample size is 3, so this should be 1/3. Okay? And that's all I need for part C. And part D. For samples of size 3, what's the probability that the average number of flows will be greater than or equal to 2? Similar calculation, but this time instead of x, I have to go for x bar because it's not the number of flows, this time the average number of flows. Okay? So I need to calculate the probability that x bar will be greater than or equal to 2. Now this can be straight away calculated using your calculator. This is our distribution. Greater than or equal to 2 means the center of that distribution is 1. 2 will be somewhere here. Greater than or equal to 2 means this shaded area to the right from 2. So we have to go to distributions and select number 2, normal CDF. And the lower limit will be 2. The upper limit will be 100,000. Mu should be equal to 1. What should be the sigma? Now this is equal to 1/3. This is variance. Variance is equal to 1/3 means sigma stands for the standard deviation in that function. So what should be the standard deviation? The standard deviation should be the square root of 1/3, which is also equal to 1/√3. Okay? Let's enter these things into our calculator.
Second, variables. Number 2, normal CDF, hit enter. The lower limit is equal to 2. The upper limit is something large, such as positive 100 million. Mu equals 1, and sigma is equal to square root of 1/3, which is also equal to 1/√3. It's easy to enter it that way, so I will enter it as that, 1/√3. Select paste and hit enter again. The required answer is 0.0416.
I got 0.0416. Okay. And then let's move on to part E. Part E says, for samples of size 3, what's the average number of flows so that only 10% of sample average number of flows will be greater than that. Okay? That means a probability is given to you. You have to do the inverse calculation. We have to use this distribution because it's about x bar, the average number of flows. Distribution is symmetric around 1. The given probability is an upper tail probability, and it's a 10%. Okay? Will be greater than that. So greater than that indicates, that technical phrase indicates that the given 10% is a right-hand probability. So this is 0.1. I need to find this value. So how do you find it? We have to go to distributions, select inverse normal, and then you can enter area. If you are using a newer calculator, you can enter 0.1 straight away. But if you are using an older version, the area of that function is always area to the left, which is 0.9 in that case. Okay? Let's go to your calculator.
So here's the calculator again. Let's go to distribution, second, variables. That's where we have distributions. This time I have to select number 3, inverse normal. Select that and hit enter. Area. I can straight away enter 0.1 as the area because in the fourth line, I can define that the tail is right. In case if your calculator doesn't have that fourth line, which indicates the tail, whether it's left tail, center, or right, you have to enter 0.9 as the area. Because in all the versions of TI-84, area stands for the area to the left. Mu is equal to 1, and sigma is equal to 1 over square root 3. 1 over square root 3. And you may also have to close the parentheses after entering square root 3, and then select the tail. The tail is right tail, select right and hit enter. Please make sure that you should hit enter. Otherwise, the tail will not be taken as right tail. Select paste and hit enter again. The answer is 1.74.
I got 1.74 as the answer. All right, and then if you move on to the next page, under point number 7, there's another question given. I will assign that as a homework question, okay? It's a similar question, but this time you have to use the uniform distribution. Daily solar radiation during the summer daytimes in Salina, Kansas is approximately uniformly distributed from 5 kilowatt hours per meter squared to 7.5 kilowatt hours per meter squared. So it's a uniform distribution. You have to know how to find the mean and variance for the uniform distribution. Okay? So I will just give you a hint. For uniform A to B distribution, what's your mean? Mean equals A plus B divided by 2. The variance should be equal to B minus A everything squared divided by 12. That's the variance. That's for the uniform distribution. I think that should suffice for you to answer all the questions of that. So I'll assign that as homework question. Okay? All right, so that's it about the central limit theorem. Thanks.